A longitudinal wave travels through a medium from left to right. Graph 1 shows the variation with time t and displacement x of a particle in the medium. So this is a longitudinal wave. So basically what's happening here is that you've got particles that are moving to and fro in that direction, while the energy of the wave, the actual wave itself, moves in that direction, but they are oscillating to and fro. And here we have on our y-axis the oscillation to and fro of a particle. So a particle will move basically this way and that way, 2 centimeters either way, like that. So state how the graph 1 shows that its oscillations are not damped. Well, basically we can see that because the amplitude remains constant. So the amplitude remains constant. I don't think I need to write that. That's pretty straightforward. So we see here the amplitude there, the maximum displacement from the equilibrium position is 2 there, it's 2 there, it's -2 there, -2 there. So it isn't changing at all. So it's not damped. Going over the page, we're going to need to keep on coming back because there's some things that we need to look at there. I've got my diagram here on a piece of paper, so you can check your piece of paper, also your actual question sheet. So calculate the magnitude of its maximum acceleration. Now, for that we need our formula, which is our definition of simple harmonic motion, is A is equal to minus omega squared x. That's actually not given on our data sheet, but from this we have omega is equal to 2 pi t. So I can say A is equal to minus. Now we're talking about the magnitude, so we can actually do away with the minus, because the minus is purely giving us a direction, telling us that it's in the opposite direction or towards the equilibrium point. So I can have 2 pi over t all squared, because that's equal to omega. So I can write this as 4 pi squared over t squared, where your t is your period. And because we want maximum acceleration, that is going to be at our amplitude, which is our x0. So we've got that. So it's a matter of just putting that all into our formula. Remember, we had our x0 is actually 2 centimeters. Now it's usually best to work in meters, so this is going to be 2 times 10 to the negative 2, or 0.02 meters. So we can put that all in there. I don't think I need to calculate it for you. It works out to be about 19.7 meters per second squared, which, when we round it down, is 20 meters per second to the minus 2. The reason why I do that is because we have 2 significant figures. We work with 2 significant figures, as you can see there, in all our values. So we put that into 2 significant figures. Calculate its speed at 0.12. Now, perhaps I should go back to the formula here, not the formula, the graph here, and just look exactly where that is. So we're looking at 0.12. Now, you've got to be careful with these scales, because here, we see here we're going from 0.1 to 0.2. So a 0.01 is actually going to be 2 blocks. So that will be 0.01, 0.02 is like that. We drop it down to over here, we get to about over there, and we take it across, we're about over there. We're getting around about minus 1.65 in that region there. When you look at that, and that would be centimeters. So we're going to need that value in working out what its velocity is. So going back to here. Now there's actually 2 formulas that we can actually use for this. We can use this formula over here, And we can also use, because my because the graph here was a cosine graph, because I started, actually let me just go back to this, let me just go back here again, sorry to do this, but just wanted to make this point. Can you see here that this, if I look at my graph here, this is actually, because we're starting off at a maximum point for t is equal to 0, this would be the defining graph for it. X is equal to x0 cos omega t, and therefore v is equal to omega minus omega x0 sine of omega t. That would be that. Now that's this formula over here, but the v0 is actually equal to omega x0. So we can use that formula, but we can also use this formula over here. Now it's two different ways. I'm going to use this one over here, but we can use both. We can work it out with both. And there's actually a third way that I'll come back and show you. So there's many ways to do this question. So let's start off with this formula over here. We got our velocity where we can work out for any point. Now its speed, we're looking at its speed. So although we're calculating velocity, we don't need the plus minus there because that just gives direction. So we can just straight away leave that out, and we're going to get x0 squared minus x squared. Now we've already worked with the omega. That's equal to 2 pi over t, and we know that our time for this is the period, and that was 0.2 seconds. And then we've got our, here we've got 0.02, and then we're going to, and that's going to be squared minus 0.0165. And we're going to calculate that, and you should get in the region of about 0.35, around about that, in the region of about 0.35 meters per second, depending on what this value was over here. Remember, we need to square that. Depending on the value, that over there could be, there's a slight range that you could get because you're reading that off the graph. Okay, so that's one way of doing it, just putting it into your calculators. Please make sure that you just put brackets and so forth in to make sure that you do that calculation correct. Okay, let me show you another way of doing this, the other way. So if I go back to here, I can say that my velocity is equal to, now I've got minus v, I can write that as x0 omega sine of omega t. Again, I haven't worried about the negative sign because that shows direction, and so I can just plug this into the formula over here. Again, your x0 is 0.02 times by the omega, which is 2 pi divided by 0.2 sine, and we're going to get again 2 pi over t, which is 0.2 times by the time that we're dealing with, which was this one over here, 0.12. And when you do that, you should again come out to about 0.35 meters per second to the negative 1, around about that. So check that out, try that formula. Now a third way that you could have done it, which would have been fine, is you could actually go to your graph. Because this is a displacement time graph, you could draw a tangent at that point. So we were looking at about this point over here, weren't we? It was around about over there. You could draw for yourself a tangent. Now remember, when you're doing this, because this is a displacement time graph, the slope of a displacement time graph gives the velocity. That's the slope. So we need to draw a tangent. Now remember, when drawing the tangent, you need to draw it as long as possible. Make sure you use a ruler for this. You draw something like that, and then you find your slope of that. Now that would be your change in t, and this would be your change in x, and from that you could get your velocity also if you wanted to do it that way. Now, where are we here? This is it over here. State its direction of motion at the time 0.12 seconds. Alright, so let me go back to this graph again. We are at here 0.12, so we're over there, so it says over here we are wanting to state the direction of the motion at that point, state its direction of motion. So we can straight away see from this that my velocity of my graph is in a positive direction. It's in that direction. So it is going to be opposite to what the displacement is. It's to the left, but it's actually moving to the right. It's actually going to be moving to the right. You can actually, if you wanted to, you could draw a velocity time graph on this. It would look something like this. I'm just going to, obviously the amplitude of your velocity time graph will be different, but if I just say drew it with the same amplitude, it would be something like this. You would have a sine graph, a negative sine graph, and that would be like this. Like that. And we can see at this point over here, the velocity is towards the right, towards the right hand side.